start recording here. Okay. So in the last class, we were looking at symmetries of the Ising model, and we had listed two symmetries. One of them was time reversal symmetry, which corresponds to flipping the sign of the magnetic field, and the Hamiltonian of the Ising model is invariant under h going to minus h, but also spins flipping sign. So SI is going to minus SI. Okay, so that is one symmetry that we had looked at, and we showed that that symmetry reflects onto the symmetry of the partition function under the switch of sign of the magnetic field. Okay. The other symmetry that we found was the sublattice symmetry, and in the sublattice symmetry, we basically said that this symmetry exists only if you have bipartite lattices, and in the bipartite lattice, what you could do is you could swap the sign of all the spins in one of the sublattice, either A or B sublattice, and if you do that, then that swap is equivalently be soaked up by switching the sign of the nearest neighbor coupling J from J to minus J. Of course, this symmetry is manifested only when the external magnetic field is 0. Okay, and this is a bit puzzling symmetry in the sense that J going to minus J would correspond to switching from ferromagnetic Ising model to antiferromagnetic Ising model, and what one concludes here is that the thermodynamics of ferromagnetic and antiferromagnetic Ising model is essentially identical in the absence of external stimulus. Okay, so that is one of the things that we looked at. Okay. Fine. Then we wanted to argue in favor as well as argue against the phase transition, and wanted to see which argument really holds good. Okay, so and the reason why we wanted to do that was because we expect phase transition from some kind of things that you observe in natural phenomena like liquid gas phase transition and stuff like that. You also see that happening in the main field approximation, but you know that the main field approximation is too crude, and you really want to know whether there exists any realistic phase transition, or they are just crossover phenomena, or something where a lot of things actually remain analytic and well behaved, and just they switch from one system to another system in a very smooth manner. Phase transition is not like that. Phase transition is something where things become non-analytic, and we saw that in the even in the mean field approximation, we see the non-analyticity develop in the in certain derivatives of free energies, for example. Okay, so so we will first argue in support of phase transition, and we had gone through this argument partly. And what we said was that you can write down free energy as U minus Ts, internal energy minus the entropy piece. And of course, entropy of the system depends upon how many eigenstates or how many microstates are accessible to the system. And so therefore, depending on the temperature, the entropy contribution would change. Okay, and clearly at high temperatures, from whatever we understand of spin systems, the number of degrees of freedom accessible to the system at high temperatures is very large, and that's why entropy would dominate much more compared to internal energy. On the other hand, at low energies, much fewer states would be accessible, and therefore the internal energy would dominate the free energy expression. And therefore one would expect that this switch over from entropy dominant behavior of the free energy to internal energy dominant behavior would be called phase transition, would generate some kind of non-analyticity in thermodynamic limit. Okay, now if you try to write down partition function of a system, then typically in the thermodynamic limit, the ground state energy or ground state configuration of the system gives the most dominant contribution, and any other contribution in the thermodynamic limit, that means in number of degrees of freedom going to infinity, is exponentially subleading. Okay, we will see this when we will look at, say, 1D easing model. Of course, we'll see that in 2D easing model also, but uh, like 1D easing model is good enough to at least understand what is happening in the system. Okay, so so because the contribution of all other states is exponentially subleading, as long as the temperatures are finite, you see, what one really needs to know is to figure out what happens to the ground state of the system. Okay, so whether the macroscopic behavior of the system is of, say, paramagnetic type, or whether it is ferromagnetic type in a spin system, is much more of a game of what is the ground state of the system than what the excited states are actually doing. Okay. So what we want to do is that our model or our Hamiltonian has several parameters. Partition function is a function of those parameters plus temperature. You could kind of slowly tune these parameters and ask, do you see a change in the behavior of the ground state of the system? Okay, good. So at zero temperature, of course, ground state is going to dominate maximally. And in that case, we want to know what happens if we change the couplings in a given set of couplings. Suppose we call that set K. Okay, we want to know what happens to the system if you start changing the parameters. Okay, now at zero temperature, we really do not have T times S factor contributing here. Okay, so therefore there is no entropy versus free energy game at zero temperature. Okay, so question is, how would you characterize phase transition in a system in which temperature has no role to play? Okay, so of course, as I said last time also, that T equals 0 is a theoretical idealization of the system, but if the temperature is sufficiently low compared to any quasi-particle excitation that you could generate in the system, then that temperature is as good as being 0, because then the system would prefer to be in ground state than exciting any quasi-particle which would require larger thermal energy than whatever is the ambient temperature of the system. Okay, so from that point of view, T equals 0 is purely kind of, theoretical construct. But if you go to an experimentalist, all that fellow would want to do is to lower the temperature of the system sufficiently such that no quasi-particle excitation can be created by thermal fluctuations. Okay, fine. So in this situation, all that can happen is that a role of ground state could switch if one of the higher energy states, typically first excited state, would cross as you start changing the parameter. So along the x-axis, we have some parameters, some coupling of the theory. And as you start changing that, your ground state, first excited state, all states would behave differently. I mean, all of them are kind of slowly changing. But if first excited state crosses and becomes a ground state after a point, then the behavior of the system as you start changing the parameter goes from this ground state behavior to that ground state behavior. From this point onwards, the blue line or whatever is that color ceases to be a ground state, and the red line takes over as a ground state. This switchover phenomena, or what is called the level crossing phenomena, is considered as a signature of zero temperature phase transition. And as I said, that this is one of the kind of happening topics in current condensed matter physics, where people are trying to study quantum phase transitions in a variety of systems. And it is called quantum phase transition simply because there are no thermal energy effects which are of any relevance at temperatures which are this low, and only fluctuations that are really available to you are quantum fluctuations of the system. Okay, and so of course there is a critical coupling at which these two states become degenerate. Okay, and beyond that, across that, you have kind of switch of state of the system. Okay.
So
Yes.
one thing they also talk about in quantum mechanics is something like quantum to classical phase transition.
Yes. Yeah.
What is that then?
Oh, quantum to classical phase transition is at very high excited state. Remember, the correspondence principle tells you that very high, large quantum numbers, those states should behave more like classical systems, right?
Yeah.
Whereas what we are looking at is the ground state, right? In the thermodynamic system, in statistical mechanics, ground state plays much bigger role. Okay, so we are like far from classical limit of the system actually.
Okay.
Okay, fine. Okay, so this phase transition for quite some time was actually called only level crossing because it was low temperature phase transition mm, for a few decades. Phase transition was always associated with transitions as you start changing temperature of the system rather than various other parameters. So there is still some literature which still calls it level crossing, uh, but I think those are still older kind of things. Okay, so we can ask a question: what happens if we have non-zero temperature? Now again, as I said, like when we say zero versus non-zero, we just means that we have sufficient thermal energy available to generate some certain excitations that a low-lying excitation that a system would have. Okay, if that is the case, then you would have some dynamics in the system which is generated by pure thermal fluctuations. Okay, so T not equal to zero is a situation everywhere actually, here also in the previous one also. It's just that those temperatures were just too low for it to generate any interesting thermal dynamics. Okay, whereas when we say T not equal to zero theoretically, we actually mean that thermal energy has some important role to play. Okay, so what happens can be answered depending upon in which dimension you are working. Okay, so the answer is clearly dimension dependent. Okay, so let's start with say one dimensions. Okay, so if you start with one dimensional system, okay, then we will see that there is no transition at finite temperature. Okay, and one way to see this is to compute a 2-point function uh, in the system, and you will find that in one dimensional system, the 2-point function goes as log of x. Okay, so and this is one of the reasons why the system does not have phase transition. Okay, so as we will go ahead, we will see why log is responsible for this behavior. Okay. Now, one important point about log function is that log x magnitude diverges both when x goes to 0 as well as x goes to infinity. Okay, so for very small x and very large x, magnitude of log x is very large. Okay, so therefore, the thermal fluctuations would destabilize the ferromagnetic order in the system. Okay, so and the reason why this happens is that the meaning of 2-point function is the following. Okay, suppose you uh, consider a spin at origin. Okay, since I have written g as a function of single variable, you assume that I have used the translation invariance of the system and picked up the spin that I want to disturb to be at origin. Okay, so suppose I disturb the spin at origin. Okay, and I want to ask what is the effect felt at distance x. Okay, and that uh, thing is a correlation between the fluctuation that is happening at origin versus the fluctuation observed at point x. Okay, so this is a 2-point correlation, right? A point at origin and point at x. Okay, this 2-point function is precisely that correlation. Okay, and what this is trying to tell you is that as the distance increases, okay, the correlation is going to increase. Okay, so that means a small disturbance at origin can become large disturbance as you go further and further away. normally if you want a system to be in good state, that effect should just die out. After a few lattice sites, the effect is not seen. Okay, if that is what happens, then we would say that the disturbance is not propagating far away, and therefore if the system is in ordered state, that means if the system has, say, all spins pointing up or all spins pointing down, then a few spins would get disturbed, but rest all system remains as it was, and therefore the system would continue to have some kind of magnetization. Okay. On the other hand, a logarithmic correlation would mean that a disturbance at one site would lead to larger and larger disturbance as you go further and further away. Okay. Of course, it produces large disturbance in a very small neighborhood also, because magnitude of log x for small x is also large. Okay. So only when you are at distances of order 1, okay, in certain units, okay, that you don't see much of a effect. Okay. That unit is a typical uh, correlation length unit, but all other spins which are inside the radius of that correlation length versus outside the radius of that correlation length, all those spins will be badly affected as you go further and further away, or go closer and closer to the spin which is being disturbed. Okay. Now that is not really sounding good, because that would mean that all the spins would start getting affected by a tiny fluctuation that you generate at a particular point. Okay. If that is the case, then it would clearly destabilize a ferromagnetic order. Okay. And if that happens, then we would say that the system actually does not have long range order. Okay. Because a small fluctuation would destabilize ordered state. Okay. Okay. So as I said, the long range order uh, is related to the scale over which the 2-point function has a significant influence compared to the lattice size, say. Okay. So suppose you have a lattice size of a few angstrom, say 1 or 2 angstrom, and if your correlation length is like, or sorry, your 2-point correlation function is non-vanishing over a distance of, say, 1000 angstrom. Okay. Now, that is still small compared to the total system size. Okay, because the system size could be of the order of, say, a few centimeters. Okay, so 1000 angstrom is still 6 to 7 orders of magnitude smaller than a few centimeters. Okay, and therefore, even if the disturbance is going to last over a radius of about 1000 angstrom, which is like roughly about 1000 lattice units, it would still be considered small. Okay, as against the logarithmic disturbance, which as you go towards the boundary of the system, closer to the distances of about a centimeter, would be much larger, because they would just grow like anything. Okay, fine. So long range order is kind of related in this way, that if the correlation is not going to last large distances, long range orders is stable. If the correlation is going to affect, then the long range order does not exist. Okay.
Sir,
Okay. Yes.
since there is, I might be taking it too seriously, but since there's some minus log x, it
Yeah.
means that uh, uh, for large x, two spins are anti-correlated.
Yes. Yeah.
And why should that be?
Yeah. So that means if the spins are correlated, it will try to make them anti-correlated, right? So we are looking at a ferromagnetic setup, and the disturbance would try to flip the spin as you go further and further away,
Okay,
right?
okay,
That is why we are saying ferromagnetic order is getting destabilized,
okay, yeah.
right? If it was
Mhm.
enforcing the ferromagnetic order by saying that, like, if two spins are in the same direction, it is better, then of course we would have been happier actually. That
Yeah,
even at longer distances, correlation is actually forcing them to be pointing in same direction. It would have been nicer, but that's not what happens. It exactly tries to kind of push it in the opposite direction and tries to destabilize the order. Okay,
okay.
fine. Okay, so what we have is that Ising model ground state is a state with either all spins are pointing up or all spins are pointing down. Okay, and in that sense, they have long range order because the entire setup looks the same. Either they are pointing in one direction or they are pointing opposite direction. Okay, now if in that system, if you have a 2-point correlation function which is falling off exponentially fast, okay, then if any function falls off exponentially fast, then you typically assign a size to such a function by saying that from its maximum value, if the amplitude drops by a factor of e, okay, then that is a typical size over which the function has good influence. Okay, after that, its influence falls off much faster. Okay, of course, entire fall off is exponentially fast anyway. Okay, but you typically assign a size by saying that if initial amplitude, maximum amplitude is say A, then A by E. Okay, whatever is the distance over which the amplitude goes to A by E, that is the distance over which that function has a significant influence. Okay, so if you have exponentially falling 2-point correlation function, then you would say that Ising model ground state would be stable because there will be small pockets in which there will be some disturbances. Otherwise, the system would still have long range order. Okay. Fine. So the way to quantify this is to do the following thing. You say that, like, suppose you have a large number of spins, which is given by the number capital N. Okay, and suppose the thermal fluctuation in the system flips small n spins out of this capital N. Okay, so we are already assuming that capital N is a reasonably large number. So, for example, if you take say a system of size few centimeters, cubic system of size few centimeters, the number of particles, say, is some about an Avogadro number, or maybe, like, 10 times Avogadro number. So something of the order of 10 to the 23, 24, and so on. Okay. In that, if you are looking at small n number of spin, where small n is of the order of 10 to the 3 or 10 to the 5 or even 10 to the 10, that number is very small. Okay, 10, because 10 to the 10 divided by 10 to the 24 is like 10 to the minus 14, right? So I mean, it's small compared to the total size of the system. Okay, so the point is that if the thermal fluctuation is flipping small n number of spins, and if small n is a finite number, okay, then in the thermodynamic limit, that means capital N going to infinity, capital N minus small n upon capital N essentially goes to 1. Okay, and if that is the case, then you would say that the system has long range order. Okay, physically this just means that if you have very large number of degrees of freedom, and if a significantly small fraction of it is behaving differently, it does not disturb the uh, the order in the system, which is dominated by much larger number of degrees of freedom behaving in a coherent fashion. Okay, is that okay? Okay, maybe I can go ahead. In case you have a question, you can ask me. Okay, so contrast this with the other situation where a finite fraction of the total spin is affected. Okay, so imagine that n is like 10 to the 24. Okay, and uh, you know uh, x times n is like 3 into 10 to the 23. That is like 30% of kind of spins are affected. Okay, which is a finite fraction. Okay, in that case, if you take this limit, thermodynamic limit, then this quantity is necessarily going to be smaller than 1. Okay, if something like this happens, then you would say that the system actually has no long range order. Okay, so disturbances of this type would destroy long range order in the system. Okay, fine. Now, in the fully ordered system, the entropy vanishes. Okay, and the free energy is given by Fn is equal to minus n times j. the entropy vanishes simply because in the fully ordered system, all spins are pointing in same direction, or all spins are pointing in the opposite direction in the Ising model case. Okay, and if you look at how many such configurations are there, the answer is just one. Okay, it's precisely one configuration which involves all spins pointing up, and there's precisely one configuration which involves all spins pointing down. Okay, there are various other configurations where you may have most of the spins pointing up, but one spin pointing down, or two spins pointing down, or something like that. But if you're looking at a configuration which is fully ordered, okay, the such a state is unique. Okay, and because it is unique, entropy is, which is a log of number of such states, it is log of 1, and therefore it just vanishes. Okay, on the other hand, free energy is just a count of how much total energy that a system would have, and we know that in our Hamiltonian we have J SI times Si plus 1 with a minus sign, minus J SI times Si plus 1. If two neighboring spins are pointing in the same direction, it lowers the energy. Okay, if the total number of particles being n, then it will lower the energy to be minus J times n. Okay, that is how the free energy would be just computed. Okay, now suppose instead of having a configuration like this, where which is fully ordered, okay, suppose we have a system which contains two domains. Okay, so there exists one set of spins. We are looking at a one-dimensional system still now. Okay, so you have a setup where a semi-infinite set of spins pointing up. Okay, so by semi-infinite, I really mean very large number of spins in one direction pointing up, and a very large number of spins in another direction pointing down. Okay, so that is the kind of setup. And this different color on the spin and dots have no value. I was just trying to draw it, and I just couldn't change the colors of these guys to black. So then it looked like it was taking too much time. So I gave up on kind of changing colors and just decided to just put this picture. Okay, so don't assign any value for these colors. Okay, so this is a setup which we would call domains. Why? Because there is a domain of all spin pointing up. Okay, in the thermodynamic limit, this is semi-infinite domain, and this is a semi-infinite domain with all spins pointing down. Okay, fine. Now we want to ask, what is the energy of this configuration? Okay, now notice one thing, that the energy of this semi-infinite configuration is same as the energy that we would have computed had we not known about this remaining half of the system. Okay, so just look at the left half of the system. So from this pointer to the left, that is pretty much a fully ordered system. Okay, so we would just write down whatever is the energy. Okay, suppose you, instead of looking at the system on the left, you look at the system on the right. Okay, that is also fully ordered system, just all of them pointing in the opposite direction, but the energy cost is same, or rather energy of the ground state is negative, so energy that we save is a lot, is the same actually. Okay, so therefore imagine this being n by 2 and n by 2, just for the argument's sake, then it would have been piecemeal factors will again give you minus n times j. Okay, both these pieces taken independently. Okay, except this neighborhood. In this neighborhood, there is some cost in energy, because Si plus 1 contributes a negative value. Okay, all spins pointing in the same direction, Si plus 1 was contributing positive, no matter whether both pointing up or both pointing down. Okay, but in this situation, we have a negative value, and therefore this contribution, okay, which I want to call interface, okay, interface between two different domains, the interface contribution is going to be plus 2j. Okay, so original energy that we counted was minus nj. Okay, this fellow is going to add plus 2j to it. Why plus? Well, the answer is that we assumed that the whole thing to be same as the fully ordered state, and decided to call the total energy minus nj. but one fellow is wrongly ordered, so therefore you should remove its energy. But because it is wrongly ordered, you should also add energy, because you'll have to, because that is a positive energy contribution, and that's why 2J getting added. Okay, so that is the answer. En for this configuration is minus Nj plus 2J. Okay, now in the large N limit, this seems like a very small cost. Okay, and therefore you would think that, like, okay, I mean, this is a configuration pretty close to the fully ordered state. Okay, but we'll see that this kind of configuration has, at least in one dimension, has an important role to play. Okay, so fine. So this is the contribution to energy, and that's why the internal energy piece would kind of take contribution of this kind. Okay, so small change because of this one pair of spins pointing in opposite directions. Okay, good. Let's try to compute what is the entropy of the system. Now remember, in the fully ordered state, entropy vanished simply because there was actually a unique configuration. So therefore there was no way of kind of summing over all possible states of that kind and taking a log of that number. Okay. In this particular case, of course, the situation is a little different. Okay. We could ask, given a setup like this, one thing that you could try to do is, you can assign a periodic boundary condition to this setup. Okay, take n to be very large, and for large n, you kind of put a periodic boundary condition if you want. Okay, now that would involve flipped spin at two locations, because if this fellow is going to meet this guy at some other point on a circle, it has to have a flipped spin again. Okay, if you don't like that, just keep open boundary condition as it is, the way I have drawn. Okay, but keep the total number of spins finite, just for the argument's sake. Okay, fine. Now, where should this interface between two domains be in a system in which you are kind of putting open boundary condition? Okay, and the answer is that whatever calculation we did, okay, to get minus n times j, did not really care about where this fellow was located. Okay, it just said that, like, there are two domains, each domain seems to be contributing same energy. Okay, same sign also, and same amount of energy. Okay, except this pair, and this pair could have been here, or could have been here, or could have been here, or could have been far out to the left or to the right. Okay, no matter where it is, the difference from the ground state would still be 2J. Okay, so therefore this location of this interface, even with the open boundary condition, would be between any of the neighboring sites. So if total number of sites are n, there are n possible locations for the interface. Okay, now that number may be n minus 1, but it is not so important, that small change. Okay, in the large n limit, it is really n. Okay, so therefore this configuration costing this particular energy, okay, what we want to compute is, for this energy, how many configurations are available, and the answer is n such configurations are available. Okay, and therefore entropy would be log of that quantity. Okay, so suddenly entropy has taken a big jump, going from 0 to some some log n. If n is large, that number is significant number. Okay, it's not like it is very, very large, but it is reasonably significant number. Okay, fine. So let's try to ask a question. What is the difference between the free energy of the interface state? That means you have a domain of spins pointing down, juxtaposed by a domain of spins pointing up. Okay, where this interface happens is something we would keep free, but it is only the interface which is going to contribute to change in the energy of the state. Okay, fine. So, but what we want to do is to ask, what is the change in the free energy between the interface state versus the fully ordered state. Okay, so let's do that. Okay, so delta F is F interface minus F ordered state. Okay, that is what Fi minus Fo is. Okay, not input or output. Okay. Uh, so, so Fi minus Fo is what we are computing. The internal energy part is going to contribute 2J because this is the interface energy. This piece is the ordered state energy. So if you write down En interface minus En0, it will just remove that and keep your with the 2J factor. Okay. Then you have a minus T times S piece, which is there for the interface, but not there for the ordered state. Okay. So that's why the change in the difference between the free energy of the interface versus free energy of the ordered state is 2 times J minus KB times T times log N. Is that okay? Is this fine? Okay.
Yeah.
Okay. So what we'll do now is that we will define a critical temperature Tc, okay, using these quantities, okay. But let's first kind of do one more step, that if the temperature is positive, okay, then because n is very large, it is this term which is going to dominate, okay. J is some finite number, and this factor is always 2 times J. It is not like, this number 2 is not going to change. We are looking at only single interface, okay. So with single interface, this is a fixed number, but if the number of sites are large, okay, the entropy is going to dominate, and therefore delta F is going to go to minus infinity, okay. Delta F going to minus infinity, okay. I mean, these are mathematical stuff, right? In the sense that, like, you take n going to infinity, then delta F goes to minus infinity. In real situation, n becoming large and delta F becoming large negative. That's all it means, okay. But what is the meaning of delta F being negative? Delta F being negative means that the interface free energy is lower than the fully ordered state free energy, right? Okay. And if that is the case, then the system would of course prefer to be in the interface state, right? Because that is one way of lowering the free energy of the system. Okay, fine. So that is the thing. The system would lower its free energy by creating an interface spontaneously at temperature which is greater than 0. Now notice one thing, that if the temperature itself was 0, then of course there was no game here. Okay, then entropy has no role to play, and you have just factors sitting around like this, and that is the zero temperature physics that we were trying to discuss earlier. That is just a question of, is there a transition from one particular type of ground state to another particular type of ground state at zero temperature. Okay, the fact that T is not equal to 0 brings in this new piece, and this new piece could dominate in the thermodynamic limit. Okay, now notice one thing, that suppose you go back to this picture, okay, and you going away from this interface far out in any direction, either this or that, doesn't matter. Okay, suppose you go in positive direction. Okay, suppose you go sufficiently far so that you have no kind of inkling that there is an interface in the system already. Okay, then far out on the right, you would think that you are in an ordered state. Okay, but if you are in that ordered state, then you can try applying the same analysis, and you will figure out that this semi-infinite spins pointing down would also prefer to spontaneously generate an interface and lower its energy, right? Lower its free energy. So it is not just that the system would want to generate one interface. It may want to generate 2 and 3 and 5 and so on, and it may proliferate the number of interfaces by doing that, it would actually lower the free energy of the system. Okay, but if there are too many interfaces in the system, means that nearest neighbor spins are actually not even pointing in the same direction, right? Just simply because the interface dominates over the order. Okay, so what you find is that system may prefer to get into a larger number of interfaces, okay, because that would have larger entropy, right? Just look at this setup. Suppose you have a up-down pair here, and so let's call this up-down pair to be at location 0 and 1. And then you have an up-down pair at location, say, 2000 and 2001. Okay, that is one configuration. But suppose you have like two such interface configuration, then locating them, one of them can be located at n points, the other one can be located at some n minus 1 points roughly, which is in the thermodynamic limit is same as n. So total number of possible configurations that you could construct with two interfaces is n squared. Okay, and therefore the entropy is much larger for two interface setup, and of course even larger for three interface setup. Okay, until you, of course, the number of interfaces become as comparable to the number of lattice sites. At that point, again, the numbers would start decreasing. Okay, but in general, finite number of interfaces in the system would have much larger entropy. Okay, it would go as capital N to the small n, where small n is the number of interfaces. And already with single interface, the system seems to be kind of preferring to go into the interface state, and multiple interface would lower energy even faster, and therefore instead of all the spins trying to point in the same direction, they would rather try to point in opposite direction. Okay, and lower the free energy of the total system. Okay, so that is what we mean by the statement that at t larger than 0, there is no long range order in this system. Okay, because of the thermal fluctuation. And this thermodynamic analysis is the one which is borne out by the statement that the 2-point correlation function goes as logarithm. Okay, that the system would generate different kind of excitations in order to lower its free energy. Okay, but in the process, it would destroy the long range order. Okay, so this is what would happen if you look at, say, one-dimensional Ising model. Okay, so let's try to contrast this with the two-dimensional Ising model. Okay, so let's consider 2D model. Okay, so I should warn you that we are not trying to solve the 2D model right now. We will take it up at some point, but at least right now we are not doing that. Right now we are just trying to do this internal energy versus entropy analysis of the system to see whether there is any chance at finite temperature for the system to have long range order, okay, spontaneously. Okay, that is the question. And what we found was that in one-dimensional system, there is no hope. Okay, now, as I think we discussed in one of the earlier lectures, that this statement is, of course, crucially dependent on the fact that we are talking about local interaction. Okay, by local I mean nearest neighbor, or maybe next nearest neighbor, or next to next nearest neighbor, and so on. Okay, finite. I mean, a few steps here away from one location is still called local. Okay, but suppose you have an interaction which is, J Si Sj, okay, and J is a function of Ij. Okay, so let me call it this way, that J is a function of I minus J. Okay, the distance between the ith site and jth site. J as a function of I. Let me not use the I and J. Let me call it M and N. J as a function of M minus N, Sm, Sn. That is the kind of interaction we are considering. And J as a function of M minus N is 1 over M minus N, suppose. Okay. Then this is like 1 over R like potential, right? So a spin at one point is interacting with spin at any distance R by inverse potential, okay, or inverse square force. Okay, that kind, if you consider that kind of interaction, which are long range interactions, okay, then what we are talking about may not hold. Okay, But if you are talking about local interactions, nearest neighbor, nearest neighbor, next to nearest neighbor, and that's it, okay, say, then whatever we have said is still true, okay. There will be, of course, some modification because there is a next to nearest neighbor interaction contributing some additional energies and stuff like that, but you can work that out, okay. It doesn't uh, totally kind of falsify the argument. But long range interaction falling as 1 over r, 1 over r squared, okay, completely fresh analysis is required, okay. Is that okay? Okay. So let's go over to 2D Ising model. So in case of 2D Ising model, uh, uh, if you have a kind of interface in the two-dimensional system, then that interface typically uh, is something which separates, say, a domain of up spins from domain of down spins, okay, is typically a closed curve, okay. Now, I said it's a typically a closed curve because you may have a domain bounded on one side by boundary of the system. Okay, in that case, of course, it would look like an open curve. Okay, but barring such situations, any domains which are inside the bulk of the system, the interface would have a shape of a closed curve. Okay, fine.
Sir, what do you mean by shape of the interface?
That means, suppose you. Okay, let's go back to the picture above. I was trying to draw for 2D Ising model also, but like it was taking just too much time to do that. Like imagine something like this, okay? This is one line. You draw another line, but instead of having an interface at this location, maybe you shift it here. And then you shift it again back to the original position. Then you would say that your interface started like this, okay? Then it kind of went to the left, then went to the right, and so on, okay? But if the domain of all downspins is finite, then this interface would kind of close at some point, okay, like that, and it will cover all the downspins inside in that domain, and all the upspins are outside. Now you may have another domain somewhere else of downspins, then it will be separated by another closed curve, okay. Is it making sense?
So basically, the boundary separating the sort of regions of down and up.
Exactly. It's a boundary which is separating, yes. Yeah. So across the interface, the spins are pointing in opposite direction. Does that make sense?
Oh, sorry, your voice cut a bit.
I said that, yes, what you said is right. I said across the interface, the spins are pointing in opposite directions.
Okay.
Okay. So that is what we call interface. In this case, the interface is just a point. Across this point, the spin is pointing up in this direction and pointing down in if you go to the right. Okay. In two dimensions, of course, you will have more such configurations because there is another line above and few lines above, few lines below, and you would kind of see a structure of that kind. Okay, fine. So now we could kind of, just for simplicity, okay, because actually, if you really think about it, ideally the interface is not on the lattice side. Interface is between the two lattice sides. Okay, right? But you could kind of, for simplicity, assume that the interface is sitting on the lattice side. Okay, that I put an interface along the last up spin across which there is a down spin at the next lattice side. Okay, and I kind of try to draw a curve along that. Okay, this is just for kind of, counting purpose, nothing very important otherwise. Okay. You could also do this counting a little differently. If you allow a link between nearest neighbor lattice sites, then you could say that number of links cut by the interface. Okay, that is the number that we are interested in right now. Okay, so instead of talking about that links, I'm just talking about the sites across which the spin is flipping. Okay. So ideally we should be really talking about links, but then I thought, like, introducing links requires introducing one more concept. So that's why I thought I'll just talk about the spins. Okay, fine. So what I was saying was that the interface is the kind of boundary of two domains across which the spins are pointing in opposite direction. Typically has a shape of closed curve in a two-dimensional Ising model. Okay. Now suppose we have n spin flips across the interface. Okay. That means you have a picture like this. Okay. And after kind of going n steps, the curve closes onto itself. Okay. So there are like n places where the spin flip is occurring. Okay. Suppose that is the setup. Okay. And n is some finite quantity right now. Then we know that every time you have an interface, the cost in energy is 2j, right? Is that okay? Because the neighboring spins are pointing in opposite direction. So differential of the interface energy versus the fully ordered state energy is 2j. Okay. Now, if there are n spins which are flipped, then it is going to cost us 2 times j times n. That is the energy cost. Okay, relative to the ordered state energy of the system. Okay, is that fine?
Yeah. Yeah.
Okay, fine. So now let us try to compute the entropy. Remember, like in 1D system, it is the entropy which is the one which was responsible for destruction of the state. Okay, let us try to compute the entropy in the two-dimensional system. Okay, fine. So in the two-dimensional system, the entropy is related to what is called a coordination number. Okay. So what is the coordination number of a lattice site? So suppose you take a particular lattice, okay, say a square lattice, okay. Then you pick any lattice point, okay, and you ask how many neighbors do you have to which this lattice point talks to, okay, if you have nearest neighbor interaction, okay, or how many nearest neighbor links it has, okay. In case of square lattice in 2 dimensions, the number is 4, okay. But if you take a triangular lattice in 2 dimensions, then the number is 6, okay, because triangular lattice would have a hexagonal neighbors, 6 neighbors to a particular point, and therefore the coordination number would be 6, okay. But you may have different kind of lattices, asymmetric lattices and structure like that, and in that case the nearest neighbor number could be smaller, okay. So the coordination number depends upon what kind of lattice that you look at, okay. But the main point here is that the entropy is related to this coordination number, okay. So uh, so why is it related to the coordination number? Because the coordination number is a number which tells you that how many nearest neighbors sites that are available to you to go from a given site. Okay, so for example, on a square lattice, if you are at one particular site, there are 4 directions in which you could go. Okay, your coordination number is 4, and if you have an interface at that location, then that interface has 4 direction in which it would go. Okay, now that is a bit of a kind of wrong calculation. We'll correct it in a moment, and that is here that if you have a coordination number z for the lattice, then the number of directions in which the interface could go is z minus 1 actually. And the reason why it is z minus 1, because interface has arrived at that lattice site in some direction, right? So that direction is already gone. Your interface cannot go back in that direction again, right? So therefore, if you along some nearest neighbor direction, if you arrive at a particular lattice site, generate an interface coming to that point, then out of z points that are available to a particular lattice point, one of them is the one from which there is an incoming interface. That interface can progress in the other direction, but that the number of direction available in that case is only z minus 1. Okay, good. So at every point you have z minus 1 such directions available for your interface to go. Okay, so it arrives at this point, and then it, out of z minus 1, it picks up any one direction for the interface to move. Okay, if you have n points on the interface, then number of possible configurations is basically z minus 1 to the n. Okay, fine. So there is a small yeah.
What is the correct configuration here? Like, we are sort of drawing an interface of n points,
Yes.
and then we are asking the question which point to choose next.
Yeah. So you say that like you're just drawing the interface. Okay. All you're trying to say is that like there are n locations across which the spin is flipping. Okay. What are those n locations you have not yet talked about? Okay. But you want to kind of draw a curve which would kind of differentiate the spins across that curve. Okay. That it would say that the spins point in opposite direction across the curve.
So
Okay.
the number of configurations is basically the number of curves that we can draw with these endpoints.
Exactly. Exactly. Yeah. Okay, so of course there is a small correction to it, because if the number is n is kind of small number, then the if the curve has to close, then the number of possibilities are not exactly z minus 1, but there is a n dependent correction to it. Okay, but that correction is a kind of subleading correction to this. So to leading order, this is a factor that is available to us. Okay, so what it tells us is that the entropy is number of such possible configurations, logarithm of that. Okay, so entropy is therefore Boltzmann constant times n times log of z minus 1. Okay, so let's try to put this back into our free energy expression. So our delta E is this. That means the ground state energy plus 2 times j times n is the interface energy. Okay, and the interface entropy is this. Okay, anyway, we want to actually find out what is the differential, so we don't even have to put in the ground state energy. The total energy is therefore the total cost in the free energy to get the interface is 2 times j times n sitting outside here minus kbt times log of z minus 1. Okay, is that okay? So this is the internal energy part, 2jn, and kbnt times log of z minus 1 is t times s. Okay, so now what we'll do is we'll define a quantity called critical temperature, which is 2j upon kb times log of z minus 1. Okay, so kb times log of z minus 1 in the denominator. Okay, let me just do that. Okay, fine. So now first thing is that, like, first comparison that we should do is, I'll just split the screen, which will be useful here now. So remember we had written down this quantity here. Okay, delta F is 2j minus kbt times log n. Okay, this was in the one-dimensional system. Okay, contrast that with what we get here. Okay, which is delta F has a factor n sitting outside. Okay, fine. So therefore, whether delta F is positive or negative is determined by t actually. Okay, not so much by n, because n is just sitting outside giving a multiplicative factor. Okay, so clearly this behavior is qualitatively different from the kind of behavior that we noticed in one-dimensional system. Okay, one-dimensional system, it is a n which completely destroyed the setup. Here this n is not so much kind of responsible for destroying or deciding whether delta F has a positive sign or negative sign. Okay, so in fact, if you take n going to infinity limit, okay, it would still not tell you whether delta F is positive or negative. It depends upon what is T. Okay. So what we will do is we will define, I just want to keep this here. We will define the critical temperature Tc to be 2J divided by Boltzmann constant times log of Z minus 1. Okay. That means, in other words, you just pull Kb times log of Z minus 1 outside. Okay. Then it gives you 2J upon Kb times log Z minus 1 minus T. Okay. You call this quantity Tc. Then you get a expression delta F is equal to Kb log of Z minus 1 times N multiplied by Tc minus T. Okay. And now you see that if you take N going to infinity limit, okay, if T is less than Tc, then F is positive, delta F is positive. And if T is greater than Tc, then delta F is negative. Okay. So that is the setup. If T is greater than Tc, delta F would be negative as N goes to infinity. Okay. Yeah. So let me keep it here. Fine. But like if delta F goes negative and large, okay, that means what? That means interface is preferred over the ordered state, right? Because delta F is the free energy of the interface minus the free energy of the ordered state. If the free energy of the interface is lower than the free energy of the ordered state, the system would prefer interface. Okay. So for temperature T greater than Tc, interface is preferred over the ordered state. Okay. Which implies that there is no long range order at temperature larger than Tc. Okay. And that is what we expect, because the system which is paramagnetic is a system in which sufficient amount of thermal energy is available for spins to point in any direction, and therefore they would not respect the ferromagnetic ordering when you have sufficient thermal energy available. And if it doesn't have ferromagnetic ordering, that means there are more interfaces in the system. Okay. So what we find is that there exists a critical temperature above which the interfaces are preferred over the ordered state. Okay. What if Tc is greater than T? Okay. In that case, the thermal energy available is lower than the previous configuration. Okay. And in that case, what we find, sorry, the formula is right here. If T is less than Tc, then this quantity is always positive, right? Because 2J minus KBT times log of Z minus 1 is a positive quantity. If this quantity is positive, that means it will cost you more energy to create an interface, right? Because this is the interface energy minus the ordered state energy. And if that is positive, that means interface energy is higher than the ordered state energy. And in that case, system would rather be in the ordered state than generate an interface, right? So that is consistent with what say a mean field result that we had obtained. Okay, namely that at temperatures higher than Tc, the system would be in the disordered state, and at temperatures less than Tc, the system would prefer an ordered state, right? Okay. So what we have concluded is that in the 2D Ising model, you would naturally see a long range order in the system if the temperatures are lower than some critical temperature. Okay, fine. So in fact, because of this long range order, that means most of the spins pointing in the same direction, there could be small fractions of spins pointing in opposite. There could be small interfaces and so on, but that is besides the point. The larger structure in the system would prefer to point in the same direction. That is the point that we are trying to make. Okay. That setup would correspond to a statement that for temperature between 0 and Tc, the system would show net magnetization. Okay. And then the statement of net magnetization implies that the system has a stable long range order. That means if you see spins pointing up in some region of the system, you can safely believe that if you go sufficiently far away, spin would still be pointing in the same direction. Okay. In between, you may find a smaller, tiny domains where spin could be pointing in opposite direction, but nevertheless, larger structure is pointing in the same direction. Okay. Fine. Okay. The other thing that we could, of course, do is that we studied the 1D Ising model and we also studied the 2D Ising model. Okay. You could ask a question, what happens if we treat the dimension as a continuous parameter? Okay. It's not something that we normally do. Okay. But it's a useful thing to do, particularly when you do, say, quantum field theory analysis. Sometimes it is useful to keep the dimension to be something like this. There's some epsilon parameter away, like 4 minus epsilon or something, or in this particular case I'm looking at 1 plus epsilon, and we want to ask what happens if I start tuning epsilon, how does the system behave? Okay. And we will not do this analysis, but it has been shown that if you look at system in 1 plus epsilon dimension, then the TC is proportional to epsilon. Okay. And that is one of the reason, I mean, that's one way of explaining that if you are in one dimension, then TC is actually 0 because epsilon itself is 0. Okay. And if you are in higher dimension, then TC is non-zero. Okay. And that doesn't require you to go to 2 dimensions, but you could go to any some fractional value and you would still see the system having non-zero critical temperature. Okay. Fine. So let's now try to give the opposite argument. Okay. So, but before I do that, is this okay with that we actually do the analysis and see that in the 2-dimensional system we do see a transition, at least theoretically? Is it making sense, or am I going too fast?
No, it was fine.
It's okay. Right? Yeah. Yeah, because we don't have one-on-one kind of this. I mean, not face-to-face discussion is not taking place. So that's why it's a bit harder for me to figure out whether I'm going too fast or too slow. Either way, you should probably tell me. Okay, so maybe I can go ahead and let's try to, let's try to make an argument in the opposite direction. Okay, so this is an argument in support of impossibility of phase transition. Okay, so now recall in the Ising model we had a symmetry which was called time reversal symmetry, and the time reversal symmetry, when we studied, we figured this out, that the free energy of the system is independent of sign of the external magnetic field. Okay, so you could have flipped the external magnetic field and the free energy would have been the same. Okay, so let's try to compute magnetization. Okay, so if we try to compute magnetization, then the magnetization in the presence of external magnetic field would be computed by this formula, which is -1 over n del f by del h. Okay, fine. But since the free energy is even function of h, okay, you could have written this equation as -1 over n del f by del h, but f as a function of minus h. Okay, since it's an even function, it doesn't matter. This statement is same as that statement, right? Is it okay? But then, given that this statement is same, you could also say that, okay, I can take this expression and I keep f of h as it is, okay, and soak up this factor of this minus sign and write down del f by del of minus h. Okay. but there is no minus sign here. Okay, but this expression is minus of the magnetization. Okay, but with a minus, but with a negative magnetic field. Okay, because you are differentiated with respect to negative magnetic field. So what we find is that the magnetization M of H, okay, is if you flip the magnetic external magnetic field, the magnetization is opposite with respect to the opposite magnetic field. Okay. In particular, if you set the external magnetic field to 0, you would expect that M of 0 is equal to minus M of 0, and therefore you would say that like M of 0 must be 0. Okay. But if the external magnetic field is off, okay, then the magnetization would happen only if the system has spontaneous magnetization, right? Like the way we argued in 2D easing model, you have a spontaneous magnetization below temperature T equals Tc. Okay, but this argument tells you that the moment you set H to 0, your magnetization just vanishes. Okay, and therefore there is no spontaneous magnetization. Okay, and if there is no spontaneous magnetization in the system, then there is of course no phase transition from say paramagnetic state to ferromagnetic state. Okay, fine. So we have, on one hand, we have argued by looking at the thermodynamic variables or quantities to show that system has to undergo phase transition. You don't have much of a choice. On the other hand, the order parameter, which is a magnetization in this particular case, actually just does not change. It does not become non-zero in the absence of external magnetic field. Okay, from this argument. So we have to find out which argument is not going to work, and of course, we know which argument is not going to work. Okay, so so this is the thing that I said, that there is no magnetization in the absence of external magnetic field. Okay, and therefore there cannot be any phase transition in the Ising system. Okay, now of course this argument is correct. There is nothing wrong with this argument the way it is stated. Okay, only problem is that this argument goes wrong when you take thermodynamic limit. Okay, and so let me say what is the problem. Okay, this statement that M of H is equal to minus of M of minus H implies that when H goes to 0, M of 0 equals minus M of 0 implies it is 0. This statement assumes that these quantities are actually analytic everywhere. Okay, and remember when we talked about convex functions and quantities like that, we said that these functions are analytic, and if when I say analytic, of course differentiable, therefore almost everywhere. Okay, it doesn't have to be everywhere, almost everywhere, but there could be points where it wouldn't work. Okay, and this is precisely the catch out here, that when you take thermodynamic limit, then even in the mean field theory we found that although Hamiltonian was an analytic function of couplings and spins, okay, the mean field values of various quantities actually did develop non-analytic behavior. Okay, so clearly thermodynamic limit is the one which is responsible for developing this non-analytic behavior, and we in fact know that the free energy in thermodynamic limit does develop cusp at when the external magnetic field is 0. Okay, so actual answer therefore is minus del F by del H. Okay, there should have been 1 or n factor, but doesn't matter. Okay, is plus M for H greater than 0 and minus M for H less than 0 as H approaches 0. Okay, so diagrammatically it is going to look something like this, that you would have expected the system to look something like this. Okay, this blue line, and if the system is completely differentiable or in fact completely analytic everywhere, then the argument that we just gave, that M of 0 should be 0, is certainly true. Okay, that assumes that not only free energy but all kinds of derivatives of free energy are also well defined everywhere. Okay, but that is not guaranteed in the thermodynamic limit. So it may happen that M at H equals 0, as H approaches to 0 from positive side, may be minus of M H equals 0, H approach from negative side, but these two numbers may not be same. They are opposite of each other, okay, but non-zero. Okay, so this is consistent with this statement that m of h is equal to minus m of minus h. If h goes to 0 from positive side, gives you m plus, and h approaches 0 from positive side here, so that minus h approaches 0 from negative side. Okay, then it gives you minus m value, which are just opposite of the first one. Okay, then you could still be fine. Okay, and this fact is the one which is responsible for the statement that in the absence of uh, external magnetic field, you have spontaneous magnetization. Okay, this is a magnetization versus external magnetic field graph. Okay, now this is something you may have done in the undergraduate lab also. Is, this is half of the hysteresis graph that I have drawn basically, right? You get something like this, it kind of matches here and then comes down like that, and it goes here, and then it comes back and then goes up from above, and this middle blue curve is the only half of that curve is the one which is available, which is visible to you when you start your experiment. You start with the setup with net magnetization 0, turn on the magnetic field, it goes up like that, and when you start reducing magnetic field, it doesn't come back along the blue line, but it comes back along this amber line, and then it comes here, and then it goes down this way and meets this blue line somewhere, and then comes back and goes along the amber line again, and it never follows the blue line. Okay, that is the hysteresis experiment you must have done. I have tried to kind of enhance this effect. It doesn't go this far out, but just to kind of uh, just to be able to do the distinction between the terms. Okay, but otherwise, um, yeah, otherwise it has directly nothing to do with the hysteresis graph. Hysteresis graph is little kind of the distances actually are highest at zero magnetic field and not at some intermediate value. Okay, so even in our case also the distance is highest at this value and not intermediate cases. But okay, don't take the diagram too seriously. But the point that it is trying to make is that you could have in thermodynamic limit m and minus m values at when the h is 0, but depending upon how h is equal to 0 is approached. Okay, so although this argument is correct, okay, this argument is correct only when n is finite. Okay, in the thermodynamic limit, when the system actually develops non-analytic behavior, where certain derivatives of f are not continuous, then in those cases, this statement does not necessarily have m0 is equal to 0 as a solution. Okay, and therefore, although this statement says that there cannot be any phase transition in Ising type systems, in the thermodynamic limit, the system actually manages to evade an argument of this kind. Okay. So what I'll do is I think I'll stop at this point and we can pick up from here. Okay. What we'll do is next time is basically try to study Ising model in the, yeah, maybe I can, let me just complete this argument and then we can. So the problem, well, not the problem. The reason why this stuff happens is because you have to take two different limits. Okay, when you take look at the thermodynamic limit of the system. Okay, the two different limits that you are trying to take are the following. You have to take h going to 0 and n going to infinity limit. Okay, and the question is, how do you take these limits? Okay, there is one way of taking this limit where you take h going to 0 first and then you take the n going to infinity limit. Okay, in that case you find that the magnetization will just vanish. Okay, but if you take n going to infinity first and then you take h going to 0, then you find that the magnetization is non-zero. Okay, so this effect is basically non-commutativity of the limits that you take when you kind of study the thermodynamic limit of the system. Okay. This phenomenon is actually called the spontaneous symmetry breaking. Okay, and the fact that m has non-zero value even in the absence of external magnetic field for temperatures lower than Tc. Okay, that is the only situation in which m is spontaneously taking non-zero value without external magnetic field. That is called the spontaneous magnetization. Okay, It is this spontaneous magnetization is what we had earlier called the order parameter, okay, because the system is in ordered state at temperature less than Tc, okay. So this is some way of characterizing what is called the spontaneous breaking of the symmetry, okay. Fine. So I think next time we'll study Ising exact solutions of Ising models. Okay. So any questions here?